Part 2 is about curve reconstruction algorithms. So first we have, I will talk about graph-based algorithms based on proximity graphs that were presented in the first part, and then about feature size-based algorithms which are able to reconstruct from features of arbitrary sizes. So here's an overview of the list of the algorithms based on graphs, which I will briefly present in the next minutes, starting from alpha shapes, which were proposed by Edelspruner in '83. So the concept is that we have disks of radius 1 over alpha. Alpha is the parameter, and this disk you can see this as a metaphor of ice cream, which is the gray shaded area. Then we have yellow chocolate chips, and we have a spoon of this radius 1 over alpha, and we are spooning ice cream, scooping ice cream from without getting any chocolate chips, and then we end up with this reconstruction. A generalization of that with alpha equal to 0 would be the convex hull, as no primitives would be removed. Bernardini and Bajaj proposed a reconstruction algorithm based on that to extract manifolds in '97, and later Bernardini et al. Proposed a famous ball pivoting algorithm for surface reconstruction and curve reconstruction. Next is the beta skeleton proposed by Kirkpatrick et al. In '85. Here we have a parameter beta, and based on whether beta is smaller or larger than 1, there is a function computed which then takes either the intersection or the union of the disk, and if these are empty, then the edge connecting the two red dots will be part of the beta skeleton. So this empty lens area is formed with an angle on the points, the 2 points and 1 on the lens, and this must be smaller than a certain angle theta, and theta is computed from this parameter. So for beta equal to 2, this equals the relative neighborhood graph that we presented in the first part. Gamma neighborhood proposed by Weltkamp in '92 is a unification of several proximity graphs, as are listed here. So here we have two parameters, gamma 0 and gamma 1, in the range of -1 to +1, ordered, and then it contains the edges with an empty neighborhood similar to the beta skeleton, which are defined by disk with a function using these parameters. You can also reconstruct shapes which are not on a Delaunay graph, so it can have edges which are not part of the Delaunay graph. That's not a subset. Next is sculpting, which was proposed by Boissonat in 1984. We have a point set, then we construct a convex hull and its Delaunay triangulation. And for the sculpting metaphor is a sculptor can remove parts from a stone by picking at its outside. So what is shown here in light yellow triangles are triangles which have an edge on the current boundary, which initially is the convex hull. And based on some criterion, we remove triangles until a stopping condition, which unfortunately original sculpting often falls into local minima, and then we may get a final boundary like this if the sampling is relatively sparse as in this point set. Figueredo et al. Proposed a reconstruction algorithm based on the Euclidean minimum spanning tree, Euclidean mean that's in the plane, and they prove that the EMST reconstructs an open curve from sufficiently dense samples. Open because the MST doesn't contain any cycles, and of course if you have multiple connect components, the minimum spanning tree, as it does spanning of all the points, will make a false connection as seen at the borderline here. Next, an algorithm we proposed in 2011 based on the EMST, and then you can see the green and blue candidate edges, which so the green ones are in the final graph, the blue ones and the red ones are candidates, so the blue ones can snap to red ones and can also be moved. So this is a set of combinatorial operations, and while it gives good results, it also has combinatorial complexity. That's not very useful in practice. In 2013 we published another algorithm which is based on the EMST, and what we do here is we first construct the EMST spanning all the points, so this resembles already the shape. Then we do the boundary complex as explained in the first part by extending EMST, which has at least one incident edge to its vertex, to at least two incident edges, also sorted by minimum length of the edges. And now we get a shape which is closed. It has an interior shown as the yellow area, but still looks deflated in many regions. So what we do now, we take the Delaunay triangulation and look for each vertex which is not manifold, meaning that when we traverse the boundary it's only visited once, which is not the case here. This vertex here shown in detail will be visited twice when we traverse the boundary. So we look at all incident triangles and we add a triangle which, when we exchange the edges, adding the triangle will add the least length to the total boundary length. We call this operation inflating. As you can see here, this gives quite good results. Then the degree of the vertices is at most 2, because some interior vertices are left. And now we apply the original sculpting step from Poissonat, which then does not usually run into local minima anymore. So here we look at all the interior vertices and its incident triangles in the Delaunay triangulation, and candidate triangles are the ones which have edges on the current boundary, and then we select the triangle which, when we flip it in the current Delaunay triangulation, so here edge is removed, 2 more edges are added to expose the interior vertex on the boundary, and it adds, we choose the target triangle that adds the least length to the boundary length. And then we get the desired result, which is also manifold, so the degree of all vertices is equal to 2. Atali proposed R regular shapes. They have a curvature of R, at least R, everywhere. However, this requires uniform sampling of the boundary, and the boundary consists of edges which are shared by Delaunay circumcircles, and property is depending on the curvature R, which translates into a certain angle. The shape holograph, which was briefly mentioned before in the first part, can reconstruct smooth curves as long as the concavity is divergent. You can see an example on the left of what is divergent. So the medial balls, which are the circles with the point on the medial axis on the center, and touching with the radius local feature size, so touching at least 2 points on the curve. And so the radius size of these medial balls becomes monotonously smaller when going into such a divergent concavity. On the right you can see an example where it's non-divergent, so you can see the medial ball is small, it becomes larger again before becoming smaller. So this does not fulfill the condition, and shape holograph cannot reconstruct this example. The algorithm basically eliminates Delaunay triangles which circumcenter outside the current boundary to extract this shape. Next is algorithm which was proposed by also by G2 Voronoi labeling. So here you can see the red dots representing samples, and the blue dots are the Voronoi vertices of the dual Voronoi graph to the Delaunay graph. Voronoi poles are the Voronoi vertices which are most far in the Voronoi cell from the sample. So it starts with one of very far vertex, classifies this as outside, and then depending on if it's on one or the other side of the half space of the point, it classifies them as inside or outside the Voronoi vertices, and you can see in the end the green Voronoi vertices were classified as inside, the blue vertices remain as outside, and then depending on this classification the shape can be reconstructed as well as the medial axis. This has guaranteed epsilon sampling as well as a bitangent neighborhood convergence. Here you can see some results for point clouds with the medial axis in green. Next algorithm was proposed by G2, call to neighbors. It connects neighbors greedily, and the heuristic decides whether curve becomes closed or remains open, and this is parameter free. It can handle open and multiple curves, also holes and outliers. So to conclude, this is the list of algorithms which were briefly presented. They often require global parameter. Good results have mostly for uniformly sampled point density, and the Delaunay graph is not guaranteed to contain the reconstruction, and the reconstruction is sometimes slow or becomes trapped in local minima. So in order to alleviate that, we will look at algorithms based on feature size, which can reconstruct features of any size. Here is the list of 8 algorithms I will briefly talk about, starting with crust, which was a seminal paper since no more uniform sampling was required for the first time, and reconstruction was just based on the size of the features and required proportionally many points. So to recall the definition of epsilon sampling given in the first part of this session, any point P on the curve has to be within a certain distance of a sample, and the distance is an epsilon fraction of the local feature size at that point. Local feature size is the distance of a point on the curve to its closest point on the medial axis. Here you can see an example where the points on the top S0, S1, S2 are very sparsely spaced because the local feature size is large. This is an example for epsilon of about 1. And on the bottom you can see a very small feature, and the points there have to be very densely spaced in absolute values. You can also see the medial axis of the curve here in the center. So crust algorithm extracts the Delaunay graph and then the Voronoi graph, and in order to reconstruct the curve. They prove epsilon for an epsilon sampling of smaller than up to about 1/4. They can always reconstruct the curve, and this conforms to an opening angle alpha of adjacent edge of a sample to about 151 degrees. So it's not a very good result yet, but it was the first very good proof for features of any size that they can reconstruct the curve. There are some improvements, for example the anti-crust of gold soon after, which extracts the crust in a single step from the Delaunay graph and also extracts the medial axis skeleton. Then nearest neighbors crust by Day and Kumar is a simple and elegant improvement of crust with a simple proof as well. First they connect the point to nearest neighbor, and then they connect to the nearest neighbor in the half space such that the angle is larger than 90 degrees. So very simple algorithm. And they prove it for a better bound of epsilon up to 1/3, that's corresponding to angles of 141 degrees. Next is conservative crust by Day et al. Conservative crust filters edges from the Gray-Bailey graph, and as you can see here, it's robust to outliers, can reconstruct collection of open and closed curves, so it does not do this false connection as crust and nearest neighbors crust do here, but it requires a parameter and also misses some sharp corners. Another algorithm was proposed by Lenz, by first starting with a seed edge, or a small edge, and then growing a probe of a certain shape until it hits a point, and then connecting this edge with a probe with the previous point. So this is able to also reconstruct self-intersections. However, it requires an angle parameter, and they claim a sampling condition, but they don't show proof for that. Another algorithm by Hiyoshi is in 2009 depends. It adapts the traveling salesman problem. Recall the traveling salesman has to visit a number of cities with least total distance. Cities are the samples here. Hiyoshi adapts this problem to even multiple connected curves. You can see here. And it since the traveling salesman problem is NP-hard, it transforms this into a maximum weight two-factor problem, which is then solvable in polynomial time. They give a proof for epsilon up to 1/3, similar to nearest neighbor crust, but they also require relative uniformity of adjacent edge lengths, so the two incident edges of a sample can have maximum factor of 1.46. Next is one of our own algorithms, half nearest neighbor crust, which is a simple variant of nearest neighbor crust, which relaxes the angle requirement. So here to show how it works, we have a point P, its nearest neighbors in order. First it connect to nearest neighbors, same as before, and then taking the midpoint of that edge, blending out that half space, connecting the neighbor that is in the white area in the remaining half space. So this we managed to prove for a much enhanced epsilon of smaller than 0.47. Another algorithm, the sphere of sig dt, which is the intersection of sphere of influence graph and the Delaunay triangulation, posted this year. So first we take this graph, then similar to the connect 2D algorithm from 2013, we enforce degree of vertices at least 2 by adding edges from the Delaunay graph with least edge length. So then we get a closed shape which may be deflated. So as next steps we add inflating as in the connect 2D algorithm to get the manifold boundary, and then we sculpt to interpolate the interior vertices in the boundary. So we prove epsilon of up to 0.5, however for uniformity between incident edges of a maximum factor of 2. If we compare the sampling conditions of the crust algorithms, remember crust had an epsilon of about 1/4, and the smaller epsilon is the more points we need in order to reconstruct this. So here we sampled a shape with the number of required samples. Nearest neighbor crust increased the bound to 1/3, so you can already see it requires less vertices. Half nearest neighbor crust has the bound which is the most relaxed up to date, 0.47, requires still less points. And as we talked before, we can replace the local feature size with the reach over a interval of the points between 2 points, and this translates into a rho, which is a function of epsilon, and this means that we can prove even a few number of samples and still reconstruct the shape with a rho up to 0.9. So for algorithms based on feature size, this was the list of algorithms we talked about, and to conclude, they give guarantees on sampling condition and they work well for non-noisy point sets. So this concludes the part 2. Now we have a small Q&A session, so please ask your questions. Thank you.